Yes. All
Okay,
good.
very good. Well, good morning, good afternoon, or good evening, depending on where in the world you are. And welcome to this session and this presentation. So this presentation is titled Foundations and Operating Principles of RF Power Amplification, and I'm Joe Staudinger. Okay, so the outline for this talk is shown here. I'll begin by discussing essentially what is the objective we're trying to achieve in linear RF power amplification. And specifically, we'll focus on linear RFPAs as they're needed in nearly all wireless communications. We'll look at some key device attributes of the transistor and how those attributes match up and play in large signal power operation, specifically looking at conduction angle, some of the metrics like power efficiency, linearity metrics, and some discussion on load line analytical methods. We'll go through a few classes of P operation, discuss their benefits, advantages, limitations, and disadvantages, and then delve into a couple of topics that are perhaps a little bit more complex. One of them being the input nonlinearities, so looking into the gate of the device is the device is nonlinear, and we'll look at some of those effects. And then lastly, PA memory, which is particularly important for linearization such as digital pre-distortion, but it also leads to even without DPD, it leads to difficulties in that there's asymmetries and sidebands or IM products and so on. And then finally, I'll summarize the results and draw some conclusions. So before I begin, I want to mention that this talk is meant to be more tutorial and set a kind of a basis for some of the concepts that will be discussed later on. So as we go through these various talks, you'll see that there's some overlap, and this is meant to be an introduction to some of these topics and provide some basis for them. So fundamentally, in a linear RFPA, the objective is really to convert a low energy RF signal into a larger one of significant power. So we have a RF input signal going into the PA, a power supply, and our objective is to create a large signal at the output of the amplifier. Some of the niceties are that we'd like the conversion efficiency to be high, so we'd like to convert as much of that battery power or line power to power at the output of the amplifier. Of course, we need to achieve the desired output power and gain. And then with respect to linearity, all of our wireless systems, whether it's mobile or infrastructure, have fairly strict requirements in terms of the linearity. And we can think of that in various ways, but in the end, we need to replicate the input signal waveform, both the amplitude and phase of that waveform at the output port with much larger signal magnitude. So if you're a little bit new to PAs, this is different in several ways. First of all, a power amplifier is intrinsically a nonlinear circuit, in contrast to an LNA. And as such, there are quite large voltage and current excursions over much of the device's IV operating space. In fact, we try to maximize the voltage and current excursions over the device's operating plane to achieve the most power we can from the device and do so in the most efficient manner we can. So backing up a little bit, let's start with the fairly standard model for a FET device. And we can divide it into two pieces. There's the intrinsic piece shown in the dotted line. Everything outside of that is referred to as extrinsic. All of the intrinsic elements, all of the capacitances, the current sources, the output conductance are nonlinear. They're nonlinear and have dependence on the intrinsic gate source voltage and drain source voltages. So in the power amplifier, we need to deal with all of these nonlinearities. They all have an effect. They're all important. And we'll start off with the current source, as it is the most dominant nonlinearity. Outside the intrinsic device are the extrinsic parasitics, are the resistances, inductances on each of the nodes that represent various effects, such as bus bars and pad capacitances and so on. But we'll assume them all to be linear at this point. So we'll begin with classic theory. And classic theory in terms of PAs begins by looking at the current source nonlinearity. So to begin, let's assume that the current profile exhibits a constant GM, so that each of these increasing values of drain current corresponds to the same delta VGS. And even though this may be somewhat simplified, and it's a very convenient starting point for PA analysis and derivations, and that the derivation problem is largely tractable. We can do this simply with some algebra without resorting to nonlinear models. And it gives us a lot of insight into the device operation. And then further, we can add to it other effects, such as capacitances or other nonlinearities, and build up to a more full, complete model of the device. So in terms of PA speak, so if you will, there's 3 points on this graph that are important. One of them being this knee voltage and Imax, so Imax being the maximum current that the device can produce. And the knee voltage, V knee, is the transition point from the triad region where the current flattens out and is constant with respect to VDS. To the right, I show the drain current with respect to VGS. The derivative of the drain current with respect to VGS is the transconductance. And our assumption for now is that between the threshold voltage and this maximum VGS value, that the transconductance is constant. All right, so if you haven't looked at power devices, here's an example of 2 power devices, perhaps more on the infrastructure side. On the left is a high power LDMOS, silicon LDMOS device. And to the right is a gallium nitride device. We can see the family of IV curves, and then the current versus VGS on the bottom 2 plots. Now, to first order, our assumption doesn't look too bad of a constant GM. The current has more of an S shape, but still to first order, our assumption of a constant GM, I think is fairly valid. Okay, so in terms of the capacitances, as I mentioned before, all of the capacitances are essentially describing the charge under the gate. So we have CGS, CDG, and CDS. These are all modeled as a function of the intrinsic terminal voltages, VGS and VDS. And to account for them in a more complete manner, we would rely on a large signal model that has a full description of both those and the IV characteristics. But again, at an earlier point here, we want to keep things tractable. So at this point, we'll assume that all of the capacitances are linear and fixed. And then as we get toward the end of the presentation, I'll talk a little bit about some nonlinear effects in terms of the capacitances. So one of the metrics that we look at quite a bit in terms of PA design and analysis is the conduction angle, defined as 2 theta. So what is the conduction angle? So the conduction angle can be defined based on the graphs on the left, where I show the IV characteristic of the device with the cutoff voltage or turn-on point at the threshold voltage V sub t. Current increases linearly up to some maximum value until we hit Imax. We have freedom of choice of where we bias the device. We can bias it above or below the threshold. And when we apply the input driving voltage, it'll create a current pulse or perhaps a complete current sinusoid. So the conduction angle is defined as that current moment where the current is on, where the device is conducting. So from minus theta in this case to theta, where I have the response centered around t equal 0. So the conduction angle is the period of the drain current waveform where the device is conducting. And again, depending on the bias point, this can vary anywhere from 0 up to 2 pi. And that value defines the class of operation, such as A or AB, B, C, and so on. Okay. So the conduction angle determines the class of PA operation. So a 2 pi, a full sinusoid, is defined as class A. Between a full sinusoid and a half rectified sinusoid is AB. B is the half rectified current waveform, and anything less than pi is in class C. So just a few thoughts on the different bias points. Class A, of course, is inherently linear, but it's the most inefficient operation in terms of conversion efficiency. Inherently, there'll be a lot of power dissipated within the amplifier in Class A operation, and hence it's not very useful in terms of a higher power PA. As we look at the power amplifiers that are applied in wireless in both the mobile side and on the infrastructure side, they're generally biased in a fairly deep Class AB operation. And this is chosen intentionally because inherently we get a better trade-off between efficiency and linearity. Efficiency can be improved significantly at the cost of a modest increase in linearity. Deep Class AB will be referred to often as well. It's a conduction angle that is somewhat larger than pi. There's really not a precise definition for it, but if we look at the quiescent current, it'll be a small percentage of the maximum current of the device, 10% or much less than 10%. Class C, of course, is a nonlinear mode of operation, but it again is quite useful in certain transmitter applications, such as in a Doherty, can be applied for the peaking amplifier, and for other transmitters such as outphasing. Again, this Class C operation can be quite useful. So the amplifier itself may be nonlinear, but when used in these higher modes, the overall transmitter exhibits a linear response. So I think it's important to look at the spectral components of the current waveform as a function of the conduction angle. And you'll see this kind of graph often published. And it gives us quite a bit of insight into the operation of the amplifier. So in this graph, I'm showing 4 components. So the blue one is the DC component, I1 is the fundamental component, 2 is the second harmonic, and 3rd is the third harmonic. So on the x-axis, I have the conduction angle from 2 pi being a full sinusoid to pi, which is a half rectified sinusoid, down to 0. And the current coefficients are plotted on the vertical axis. So the first thing to note is the fundamental current I1 is the same for both a full rectified waveform and for a half rectified waveform. So in Class A or Class B, we would expect similar output powers. There is a point in Class AB where the conduction angle is greater than pi. The power actually goes up, or the current component of the fundamental value actually increases. And as we, again, look at Class B and compare it to Class A, we can see that the current component is quite a bit lower in Class B than Class A. So we have the same fundamental component, but a lower DC value, and hence we would expect higher efficiency in Class B. And then as we move from a conduction angle of pi lower into Class C operation, we see that the fundamental component decreases and the DC component also decreases, meaning that the device will create less power with a smaller conduction angle, but inherently it's going to be more efficient. The other point to note from this graph is that we begin to see harmonic currents. For any conduction angle less than 2 pi, there is harmonic currents, and those harmonic currents become increasingly significant as we go to lower and lower conduction angles. Now, a brief view of the drain source voltage. So again, at this point, we're only considering the current source nonlinearity. So I show schematically here a partial diagram including the output section of the device with the intrinsic elements, the extrinsic resistance, inductance going off to a bias and output matching circuit. So the impedance presented at the device can be defined with basic circuit concepts. So we can define an impedance at the intrinsic drain terminal Z sub L as a function of N, where N is the harmonic index, 0 being DC, N is the fundamental, 2 would be second harmonic, and so on. So we can define the impedance at that point as a ratio of the voltage, spectral voltage to spectral current, and then convert between the frequency domain and time domain based on the simple series expansion that I show below. So the time domain voltage that's developed on the intrinsic drain terminal will be equal to the supply voltage VDD, assuming no resistive losses between VDD to the intrinsic node, minus the product of the current and the impedance at the intrinsic node, and then accounting for the phase of the loading as well. So again, we can fairly easily go between the frequency domain and time domain, and it illustrates the concept of the ZL being the loading that's presented to the device. The other point I want to mention again is that we have freedom with the output matching network to force any impedance at the intrinsic device that we want, both at the fundamental and the harmonic. We simply need to overcome the effects of the output conductance, output capacitance, and any parasitics in the device, but we have freedom of choice to create any impedance we want at the intrinsic device, again, at both the fundamental and the harmonics, and that will lead to very useful classes of operation. So the load line, again, which is a common term used in PA analysis and design, is simply the relationship between the drain voltage and drain current. And looking at the model, there's really 2 points we can talk about. We can talk about the intrinsic drain terminal, which is defined right at the current source, or the extrinsic one, which would be more at the terminal of the device, so the metallization of the device. The current and voltage waveforms at these 2 points are quite different. They're different because of the components that are between them. So in PA design, again, it's generally we want to focus on the intrinsic drain terminal and look at that response with respect to the IV characteristics of the device. In general, most large signal device models will give us access to the intrinsic device node. And if not, there are methods of de-embedding out the extrinsics to approximate what the intrinsic voltage and current are. So again, looking at our equivalent model, the intrinsic load, ZL, at each of the harmonics is defined as the ratio of the spectral voltage to current values. And we can recreate the time domain waveform based on the current spectral components and the impedance ZL sub n at each of the harmonics. So in this nomenclature, 0 is the DC component, 1 is the fundamental, 2 is the second harmonic, 3 is the third harmonic, and so on. So let's look at a few modes of operation. Class B load line. So in this case, we bias the device at the threshold value. So the current waveform is naturally going to be half rectified. If we look at the Fourier components of the current, we find that there's a DC component, fundamental, and then even components. So something at the second, fourth, sixth, eighth harmonics. We can create a sinusoidal drain source voltage by simply terminating the higher harmonics. So if we terminate the higher harmonics, second, fourth, sixth, etc., at a low impedance, ideally a short impedance, the drain source voltage is forced to be sinusoidal. And we get the waveforms that are shown on the right, where the current is the half sinusoid, the voltage is sinusoidal, going between the knee and 2 VDD minus knee. And if we plot the ratio of voltage to current at each point in the time domain, we get the load line shown in the middle graph, where the load line goes from V I max down to VDD, and then stays 0 in terms of current up to a VDS value of 2 VDD minus the knee voltage. So Class B load line ideally would look as shown here. And this is only created if we can apply the proper harmonic terminations at the second, the fourth, the sixth, and so on. So in many PA descriptions, a comparison is often made to Class B, and this would be the reference for Class B operation. Class B, again with a constant GM device, will exhibit linear input-output power relationship. So an increase on input power leads to a correspondingly increase in output power. So it's a dB per dB relationship. Some of the other useful metrics are shown in this graph here, where I show the characteristics as a function of drive level. So V out, the output voltage, ratio to the maximum output voltage. So power increases linearly. The efficiency also increases linearly. So neglecting an E voltage, the maximum efficiency goes to pi over 4, or about 78%. This dissipated power is shown in red, and it peaks and then decreases as we drive the device under full operation. And then down below in a table, I list a few equations, some values, and also show the term alpha, which accounts for the knee voltage. Okay, so Class B is somewhat idealized. In most useful PAs, we operate them in Class AB and fairly deep AB. So at this point, I want to deviate slightly from our linear current source and note that all devices have a subthreshold region. The current does not go from 0 to increasing at an abrupt point, as my model to date would predict. There's a subthreshold region where the device gradually transitions from being off to an on state, such as I've shown here. So all devices exhibit this behavior. And again, if you describe a current source based on this subthreshold region, you'll find that the gain response is not linear. If we bias it quite deep in the subthreshold region, the gain response will increase. You'll have increasing gain with drive level. And as we bias it less deep in AB, we'll find a point where the gain is fairly flat with drive level. So again, there's the intent here is to intentionally point out that the subthreshold region is quite important, and there will be a point deep in the class AB bias where the gain is fairly constant. All right, class C operation, again, is a very useful mode. This is quite useful, especially for the peaking amplifier in a Doherty. So in class C operation, we have a conduction angle less than pi, and we'll find that the current components are all present. There's a DC, a fundamental, and all of the harmonics are present, both the even and the odds. It is possible to get much higher efficiency than class B, assuming we terminate the harmonics appropriately. So the pictures down below simply show the waveforms, the current pulse being less than pi, so 2 theta is less than pi, and the gain response for various conduction angles. So again, as the conduction angle gets smaller, we have more of a increasing gain with drive level. This next brings us to several classes of power amplifiers that are formed by applying the appropriate harmonic terminations on the output of the amplifier. So class F is a mode that is quite common. In class F, the idea is to produce a half-rectified current waveform, which is largely produced by biasing the device near the threshold voltage, and then to create or try to create the best we can a square voltage waveform. So the harmonic components of the current, there's current components present at the fundamental, second, fourth, and even terms. All of the odd harmonics in the current are 0. So we can approximate a square waveform in the voltage domain with the appropriate terminations on the device, on the intrinsic device, being a real impedance at the fundamental. We short the evens, open the odds, and as we account for more and more harmonics, our approximation of a square waveform becomes better and better and better. In the limit, there is no overlap in the time domain between voltage and current, and in such a case, the device would be 100% efficient. In practice, we can only account for a few harmonics, perhaps the second and the third, and our voltage waveform will not be as square as I've shown here, but we'll still see a nice increase in efficiency above what class B would provide. Further, this has a linear input-output power relationship. Class J is one of the perhaps more recent additions that spans back perhaps 15 years or so. Here, the idea is that we want to account for the output capacitance CDS and allow the loading at the fundamental component to the device to be complex, be either R plus JX or R minus JX. So it gives us an increased design space. We still want to bias the device to create this half-rectified sinusoidal current. So similar to class B, this has a linear input-output relationship, power relationship. But the cost of doing so is that the peak drain voltage is higher than what it would be in class B. So here in class J, the peak drain source voltage can approach 2.9 times VDD. And there's two solutions for class J, and I show what they are in terms of the impedances at the fundamental second and third harmonic. And again, they relate back to the Class B analysis before, where RL is the value we'd have in Class B operation. There are also continuous mode of operation. So this is Class BJ. And what we find here is that there's a continuum of impedances at the fundamental and the second harmonic that give us the same power and efficiency as Class B or Class J. The fundamental varies around a circle of constant R. The second harmonic is at the edge of the chart, and the third harmonics and higher are assumed to be shorted out. Again, all of these different solutions
Joe, we can't hear you. Hello, Joe. Do you hear me?
Yeah, I think we lost his connection.
Oh, I see. Okay.
No, not sure.
Yeah, it seems it's frozen.
Yeah.
Maybe let's wait.
Let me see if maybe I can send in a message.
Yeah.
So I'm not sure if maybe we can wait a little bit and maybe pass to the next speaker. If not,
Just a few more minutes. I'm trying to contact him. Let's see.
okay, yeah, sounds
Because
good.
I'm not sure that he might be still presenting, but doesn't know.
Yeah,
that
maybe he's not
nothing is
aware
changed.
that
Yeah.
we lost his
So,
connection.
because he still seems online, but
Yeah.
yeah. Okay. So hello everyone. Actually, we got Joe online again, but some technical problem. He will be talking over the phone while I am going to share the screen. Just a moment. So Joe?
Yes.
Yeah, we are on slide 18, where we didn't hear you after that.
Okay. So again, I apologize for this. Zoom seemed to have completely dropped out, so you could advance the slides for me. So let me start on 18. So Class J is a very useful mode of operation. Here we again apply harmonic terminations, but the advantage in Class J is that the fundamental loading is not restricted to being simply resistive. Here we allow the fundamental loading to be reactive, either R plus JX or R minus JX. And then there's a corresponding second harmonic termination, which is either positive or negative reactance. So we have an expanded design space, and this also allows us the possibility of folding the output capacitance CDS within the part of the matching network itself in terms of arriving at a solution. So the solutions, there's two solutions for Class J in terms of the fundamental and second impedances. And the third, of course, is assumed to be zero, to be shorted out. So with everything, there's advantages, disadvantages. So in Class J, the disadvantage is the higher drain source voltage that can result, which is about 2.9 times VDD, which is higher than what it would be in Class B. But again, we get all the benefits of Class B in terms of the same power and same efficiency. But here we have a wider design space. So moving to slide 19. There's also continuous modes, and there's here I'm simply looking at the Class BJ continuous mode. There's others beyond this. Again,
Could
this
you
relies
share your
on
slides,
appropriate
please?
harmonic terminations.
Joe, just a moment. Can you pause? Yeah. What do you say? Why I can't share? So I'm sharing this, right?
Yeah, at the bottom of the screen, you have a button, green button, in which you can share
yeah.
the screen.
I'm selecting. I'm trying to screen share. Yeah. Do you see it now?
I think it's coming. Yeah, now we can see it. Now we can see it.
Okay,
No
go
problem.
on. So, Joe, yeah, continue on slide 19. So, sorry everyone for all the inconvenience.
So here we'll just focus very briefly on Class BJ. There's other continuous modes as well, but here we have a continuum of impedances at the fundamental and second harmonic that result in the same efficiency, same power as Class J or Class B. So we have a wider design space. The fundamental impedance is shown here in red. It varies along constant R. The second harmonic impedances are on the edge of the chart, ranging from some minus JX value to 0 to some plus JX value. Third harmonic is shorted out. So Class BJ gives us a series of waveforms that have the same power efficiency as Class J or Class B. So essentially we need to choose or implement the appropriate pair of fundamental and second harmonic terminations. And we'll achieve one of these waveforms that gives us the same power and efficiency. So again, it widens the design space considerably from the Class J or Class B operation. Slide 20, please.
Yeah.
All right, so today we've neglected some of the other nonlinearities in twice. One of the more important ones is the nonlinearity CGS. So CGS is the drain gate source capacitance. And for a GAN device, you'll find that this changes quite a bit depending on bias. So when the off state to on state, the value of CGS increases quite a bit and can easily be a factor of 2 to 1 or even more depending on how the device is made. So under P operation, the device will, input signal will drive it across this range, and it will create significant nonlinear currents affecting the drain source voltage, and the drain current. So it is a significant contributor to performance in the power amplifier. However, if you could move to slide 25 for a moment. First I got a slide out of order here.
Yeah, slide 25.
Okay. So just to illustrate what the effect is, this is a simple harmonic balance simulation where I designed the device to be in tune Class B. So I create a real impedance at the fundamental. I short out all of the harmonics, and I simply vary the angle of the second harmonic near the edge of the chart. And in the graphs, I show performance, output power, efficiency as a function of the conduction angle, or not the conduction angle, but the angle of the second harmonic. And we see there's a region around 145 degrees or so where performance suffers significantly. We see a huge dip in both the output power and the efficiency. So in a point on the graph M1 where performance is quite good, our load lines look quite nice. We see a very close load line, and the VGS value is nice and sinusoidal. When we get to M2, we see that the load line is seriously disturbed. Our drain source voltage, intrinsic drain source voltage, does not look like a sinusoid anymore. So again, this is an important nonlinearity that needs to be considered, particularly in a GAN PA. If we move back to slide
22.
22. So a couple of other metrics that are important in PA. So one of them is the gain response. So the gain response is the function of drive level. This is referred to as AM to AM, so amplitude modulation to amplitude modulation. Ideally, we would like this gain response to be flat, so gain stay flat with increase in drive level until we hit compression, at which point the gain begins to compress. I show a couple of responses here. So the bottom left one is a fairly constant gain. The one to the top right is shows decreasing gain with drive level, and the bottom right one would be more representative of a Class C amplifier. So ideally, we want the gain to be flat, constant with drive level, and then compress. And in the compression region, we can define some compression points where the gain has dropped 1 dB or 3 dB. These are common points often referred to in PA design or device operation. Moving to slide 23.
Yes.
Another important one is AM to PM, so amplitude modulation creating phase modulation. So a change in input signal amplitude causing a change in output signal phase. So ideally, we would like the output signal phase to remain unchanged with input drive level. It won't. It will change with drive level. The response is quite arbitrary. It can be monotonic, non-monotonic, increasing monotonically with drive level, decreasing with drive level, or non-monotonic. But again, ideally, we want this to be constant. And in terms of metric, we often define a delta for small signal operation to a point of compression such as P3dB. Moving to slide 24.
Yeah, 24.
In most of these systems, we look at adjacent channel leakage ratio, which is a measure of distortion by applying appropriate modulated signals at the input of the amplifier. So the input signal can be described in terms of the equation shown there as an amplitude modulation A and a phase modulation B. So again, focusing just on the fundamental, there's harmonics as well, but focusing simply on the fundamental term. The output will have the same form of the envelope signal A and a phase modulation component P of T. But this amplifier is linear, the ratio of the envelope components A in, A out is constant. And the difference between the phase modulation on the input output, again, should be constant. There should be a constant difference in phase. So we can begin to visualize how the AM to AM and AM to PM will cause distortions. Any and will affect the output envelope term, and phase will affect amp will affect the phase term. So this results in increased or new spectral components outside our main channel, and the ratio and the power of these adjacent channels or alternate channels to that of the main channel with some appropriate filtering applied depending on which system we're operating in is defined as the adjacent channel leakage ratio. Moving to slide 26.
Yeah.
All right, so the last term I'll talk a little bit about is PA memory. And this is very, very important in digital pre-distortion. Its effects also show up without pre-distortion as well. So in this diagram, I'm illustrating on the left, the input is the input envelope of the modulated signal going into the PA. On the output is Y, which is the output envelope signal. And what we'll find is that the output envelope signal at time t sub n depends on the input signal at t sub n plus previous values of the envelope signal. So the output signal has a memory component depending on the current value of the input signal plus past values. So in terms of digital pre-distortion, we talk about fading memory in terms of how many time samples need to be considered to describe the current output waveform. And our amplifier fortunately has this term fading memory, and that there's a certain number of tabs or certain number of past samples that we would look at to approximate or to estimate or model what the current output voltage is. In terms of the gain response, so with a CW signal, we would get simply a gain response shown in red. With PA memory, there isn't a unique gain response. It depends on where we look in time at the input and output signals, and we'll get this cloud of points in terms of a gain response. So PA memory comes from numerous places. There's both short-term and long-term effects. There's the electrothermal effects within the device, the heating of the device of components. Short-term things occur on the time scale of the ranging from the modulated signal, the carrier to the envelope. Long-term effects can be seconds or many seconds. So they're related to device characteristics themselves, trapping mechanisms, electrothermal effects. They're also related to design effects. So things like our filters, capacitors, terms, etc., introduce storage, and these need to be designed properly to minimize memory effects. So lastly, if we go to the summary slide, again, review some key device metrics with respect to large signal operation, conduction angle, load lines, a few classes of PAs, noting their advantages and disadvantages. And again, PA designs, different nonlinearities is particularly important, and we need to be aware of it. And it needs to be part of the design cycle. And PA memory effects, especially in wireless systems, are very important. They're important and factor often a limit in how well we can pre-distort something. And even we'll see their effects creating unequal spurious components on the lower versus upper side base. So that's it. Thank you very much. I apologize for